Welcome to section 2.4, day 3, complex zeros. Today's objectives are to use the fundamental theorem of algebra and to find the complex zeros of polynomials. So first off, the fundamental theorem of algebra. So polynomials of higher degree can have complex zeros just like we did when we did quadratics. The fundamental theorem of algebra allows us to make a statement about the number of zeros for any polynomial. So we have a polynomial degree of n where n is greater than 0. There's at least one zero, real or imaginary, in the complex number system. So a corollary to this is a polynomial function of degree n has exactly n zeros. So if you have a power of 5, that means you will find 5 zeros. Some of these will be repeated, and some will be in the complex number system. So one of those things to remember here in the fundamental theorem of algebra is it says it'll be in the complex number system. Well, hopefully recall that the real number system is actually a subset of the complex numbers. So all of our real solutions are actually also complex solutions where we have a 0i. So that's another way to look at it. So if we have, whatever we have a power of, if it's n greater than 0, we will have that many zeros between real solutions and complex solutions. So by stating this factor theorem and including all of our real and imaginary zeros, when we use the fundamental theorem of algebra, we can do what we call the linear factorization theorem. It means that we can break down our polynomial into all of its factors, both real and imaginary. So what we can do with this, is we're going to do this today, is we can find all of our real zeros, and we're going to find what we call an irreducible quadratic factor quite often. If we get an irreducible quadratic factor, which means we have like x squared plus 1, or we have a quadratic we can't factor, what we do is we use a quadratic formula or other algebra techniques to find the solutions for that quadratic that we can't factor further. And then once we have all of these factors, we can write them as x minus whatever the solutions are. And we will have as many solutions as the power of the polynomial. All right, we're going to show you this later as we go through the slides. All right, the conjugate root theorem. So whenever a polynomial has a root that's an imaginary root, a plus bi, or a complex root, where b does not equal 0, that means there's a imaginary part of the solution, then its complex conjugate is also a root. So if we have a plus bi, a minus bi is also a root. So what this means is that complex roots are always in pairs. You can never have just one of them. There's always even numbers, 2, 4, 6. This is why when we did Descartes' rule of signs, for real solutions, we subtracted 2 from it. When we had we could have 4 possible positive solutions, or we'd have 2 possible positive. It's allowing for these complex zeros to happen. Because complex zeros come in pairs, you have to subtract 2 if there's a set of complex zeros. Here it says to write a polynomial function of least degree with real coefficients in standard form that has these as zeros. -1, 2, and 2 minus I. Well, what we just did when we talked about the complex roots having to have the conjugate, that means that because 2 minus I is a 0, we know that 2 plus I must also be a 0 because they come in pairs. So you have 2 imaginary or 2 complex solutions for this. So using this linear factorization theorem, we now have the solutions of -1, 2, 2 minus I, and 2 plus I. We can write a polynomial function as in factored form. And then what we're going to do is we're going to take this factored form and actually create a polynomial out of it by multiplying everything together. So polynomials come in the form of a times and then x minus the -1 because we have the solution -1, then x minus 2, then x minus the 2 minus I, and x minus the 2 plus I. So we write this like this. The a is just some constant that we multiply the entire thing by. We could double it, triple it, multiply by half. All right, we can do this. So we could make the a anything. And so I would recommend you always make the a 1 if you have a choice. We can make it anything but 0, actually. So choose 1, the a becomes 1, and we're just going to get our polynomial that we get when we multiply all the factors together. You should hopefully notice that I put in parentheses around my 2 minus I and my 2 plus I. Be careful with this because you have to be careful with your signs. That is why I put them in parentheses. So now we're going to go to the next page. It's going to show you the algebra of how we put this all together step by step. But first we have f of x equals 1. That's our a. X plus 1, x minus 2, and then we have x minus 2 minus I and x minus 2 plus I. First thing I'm going to do is I'm going to take those two first factors, x plus 1 and x minus 2, and I'm going to multiply them together. And since we're multiplying by 1, the 1 sort of just goes away because 1 times anything is just what you have that it's multiplying against. So we take this, multiply together, we get x squared minus x minus 2. I'm bringing down the other part to be with it. Now it is underlined in pink. So I'm going to distribute the negative signs. When you distribute the negative to the 2, you get negative 2. A minus minus I is positive I. Then if the next one I distribute the 2, I get negative times 2 is negative 2. Negative times a positive I is negative I. So I've distributed the negative sign. From here, I'm going to multiply x minus 2 plus I and x minus 2 minus I together. That's what's underlined in green. When we do this, we get 9 terms. You take the x times the x times the negative 2, x times negative I. You do that for each element in the first trinomial there, x minus 2 plus I. When you do this, you get all these factors, or all these terms, and we're going to combine all of our like terms. If you do this properly and you have the proper signs, all your I terms will go away. And hopefully recall that negative I squared, the one at the end, I squared is a negative 1, a negative negative 1 is 1, and you're going to add that to the 4. That's how we get the 5 at the end. So we do this whole thing, we should get into a quadratic, x squared minus 4x plus 5. That is not factorable, and it's irreducible. We can't factor it. The only way to solve this is to try to use a quadratic formula. So now we have two trinomials, quadratic trinomials, that we need to multiply together. And again, we take the first term times all the 3 terms in the second grouping. Do the same thing with negative x, the same thing with negative 2. Fully distribute. You get 9 terms again. And then we combine our like terms. And when we finish all this up, we get x to the 4th minus 5x cubed plus 7x squared plus 3x minus 10. This is a polynomial that represents those 4 solutions we started with at the beginning. This is a lot of algebra to do. You do have to do a couple of these on your assignment where I give you the zeros and you have to figure out and put it together. I give you the solutions and you create the polynomial from it. This is how you do it, step by step. Yes, you have to be careful with your signs. All right, so that's creating a polynomial from your solutions that you're given. So here it says factor and find all the zeros of a polynomial function. So first thing it says is write k of x as a product of linear and irreducible quadratic factors. Then after we do that, we find complex zeros. So here is my polynomial. K of x equals x to the 5th plus x to the 4th minus 13x cubed minus 23x squared minus 14x minus 24. And I am going to factor this. So what I need to do first is I'm going to list all of my possible real zeros. So you take all the factors of 24, plus or minus 1, plus or minus 2, 3, 4, 6, 8, 12, and 24. So those are the possible factors that we can get, real factors. Those are real zeros that are possible. Then, using Descartes' rule of signs, we're going to see how many positive and negative zeros we could have. So if we look at our initial, we have x to the 5th, x to the 4th. Then we have a sign change from x to the 4th to minus 13x cubed. So there's one sign change there. All the rest of the terms are negatives. So we have one sign change. That means we have one positive real zero. We will find a positive real zero for this one. We have to have one. I'm also going to look for what happens when we put a negative x to see what possible negative zeros we might have for real zeros. Put in the negative x. I substitute it in for every term where x is, and I simplify. We get negative x to the 5th plus x to the 4th plus 13x cubed minus 23x squared plus 14x minus 24. And then we look for our sign changes. We have a sign change here, we have a sign change here, we have a sign change here, and here. We have 4 sign changes. Since we have 4 sign changes, we can have 4 real zeros for negatives. We could have 2 or we could have 0. Remember, we subtract 2 because we could have complex zeros in this solution. We've listed our possible factors. We found out how many possible real zeros we have for both positives and negatives. And now we're going to use our lower and upper bound tests. So here we have, again, our polynomial with all of our possible real zeros listed. And we are going to find upper and lower bounds. And what we do is we pick some number. Today on your assignment, you can still use your calculator, but we have to learn how to do this without a calculator. So I'm going to show you that right now. How do we do this without a calculator? And why do we do all these tests that we have? So let's look for a lower and an upper bound. Let's do that first. So we pick some number in our possible solution set that would be a good bound to check. And it's up to you which ones you check. I try to split this thing in the middle, so roughly half of my terms are above and half are below. One of those things that should help is that we are multiplying. Our last term is negative 24. So to get to negative 24, when you're multiplying things together, you have to have relatively small numbers. So most of our solutions are probably going to fall in that 1 through 4 range. So let's find our lower bound. And I am going to start with roughly halfway through, which is negative 6. So I'm going to use synthetic division and see if this is a lower bound. So we have 1, 1, negative 13, negative 23, negative 14, negative 24. And I do synthetic division to see if this is indeed a lower bound. So we get 1, we get negative 6, add together, you get negative 5, we get positive 30, we get 17 here. Multiplied together, we get, let's see, this is 42, 40, and that's 102. That'd be negative, so negative 125. Multiply that by negative 6, we get 3, let's see here, 750. We add this together, we get 736. We multiply this by negative 6. We multiply negative 6 times, negative 6 times 6 is 36. Then we have negative 18 and 3 is 21. We have 42, 44, 16. And then we add these together, you get, it's a big number. It's going to be a negative number because this is negative here, by the way. This is negative 44, 40. So if you look at this last line, we alternate signs, which means that negative 6 is a lower bound. All of our numbers must be higher than it. All of our negative solutions. This also check negative 6. We know that negative 6 is not a solution. This leaves 4 possible negative solutions, negative 1, negative 2, negative 3, and negative 4. Now we're going to check for an upper bound. Since I use negative 6, I'll use 6 for an upper bound. Now we're going to do the same thing. We're going to plug it in and see what happens. And see if it is an upper bound. So we're going to do our synthetic division again. We bring down the 1, we get 6. We add together, you get 7. Multiply, you get 42. Add together, you get 29. This is multiply together, you get 54. 12 and 5 is 17. This is 151. Multiply by 6, you get 6. You get 30. You get 906. Add these together, you get 892. Multiply by 6, you get 12. 54, 55. And then 48 and 5 is 53. If I'm doing this math in my head right, we get 5328. If you look at the last line, every number is positive, so we know that 6 is an upper bound. When we find these bounds, there could be another number that is actually another upper bound that's lower than this, but we know that 6 is definitely an upper bound, that no numbers higher than 6 can be a solution, and we also know that 6 isn't a solution. So what we are left with this after we do this is we're left with these possible solutions: plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 4. Those are the 8 possible solutions. We have wiped out these 6, and we've actually wiped out 6 because we checked both negative and positive. We are just left with the first half. We've wiped out half the solutions. Now from here, we are going to start checking other solutions. I've got to erase this because I'm running out of room. But we know that our negative 6 is our lower and 6 is our upper bound. So from before now, we know we have these bounds. Our bounds are from negative 6 to 6. We know that these are not solutions. Okay, so we're going to test these. We also know that we have a positive solution, and either 4, 2, or 0 negative solutions. So then the question, which one do you want to find first? Do we want to look for negative solutions first or positive? Well, there's a better chance of finding a negative solution since we're going to have either 4, 2, or 0. So I would probably try for a negative solution first. And then it's just a question which one you want to try first. It's your call. We could try -3 or -4. I'm going to try -3. We'll see what happens. This sort of splits it up again. So you have -3, we're going to plug it into 1, 1, -13, -23, -14, -24, and we test. We bring down the 1. Multiply it, we get -3. We get -2. We multiply, we get 6. This is -7. -7 and -3 is positive 21. We have -2. -2 is, this is 6. We have this, multiply or add together, get -8. -8 and -3 is 24. 0. So we know that -3 is a solution. Now we have x plus 3, and then we have x to the 4th minus 2x cubed minus 7x squared minus 2x minus 8. Looking at our new polynomial there, x to the 4th, you may notice that we now have 8 as our last number. That tells us that it has to be factors of 8 that will go into this, which means that positive 3 is not possible. So now positive 3 has been wiped out. We know positive 3 is not a solution. So we can cross out -3 and 3 because we know that -3 is a solution. We know that positive 3 cannot be a solution. And then we go through again. We have one negative solution, means we have to have at least one more. And then it's a question which one you want to check. It's a crapshoot at this point. We want to get to -8. I'm going to try -2, I think. Just keep working my way down. So we plug in -2. Now we have 1, -2, -7, -2, -8. And we do our synthetic division. Bring the 1 down, we get -2. This becomes -4. -2 and -4 is positive 8. Add together, we get 1. 1 times -2 is -2. -2 and -2 is 4. -2 times 4 is negative. There's -4. -2 times -4 is positive 8. And we get 0. We have another solution. So now we have x plus 3. We have x plus 2. And we have x cubed minus 4x squared plus x minus 4. You may or may not remember how to do this, but if we have a cubed function that has 4 terms, we can always try to factor it by grouping. And sometimes you'll notice what's going on here, that we have x cubed minus 4x squared, and then we have an x minus 4. So we can factor this by grouping. And if you recall, you do this. X cubed minus 4x squared is one group, plus x minus 4 is the other group. Just like we do with the AC split, we have grouping. We can pull out an x squared. We get x minus 4. We can pull out a 1, and we get x minus 4. So this then becomes x plus 3, x plus 2, x minus 4, and x squared plus 1. This is my factored form so far. We have 3 linear factors, and then we have a irreducible quadratic factor at the end. The x squared plus 1 is an irreducible quadratic. We can't factor it. We can solve it, but we can't factor it. And if you have an irreducible one, quite often you will get a complex 0. And if you solve this, you set it equal to 0. X squared plus 1 equals 0. So x squared equals -1. You take the square root of both sides. And if you recall what the square root of -1 is, you're going to get x equals plus or minus I. I got to erase some stuff again so we have room. So with these factors, we have plus or minus I. We can rewrite now our factored form using those factors. So we have x plus 3, We have x plus 2. We have x minus 4. We have x plus I. And we have x minus I. This is my completely factored form. Has all 5 factors in it. Notice we have a power of 5. We have 5 factors because we have 5 solutions. Whatever the power is, that's how many solutions we have to have. You might have repeating solutions where you have multiplicities, but you must have as many solutions as that power that you start with. If we were given the solutions, our solutions are -3, -2, 4, I, or negative I, and I. These are my 5 solutions, and above it is the factored form. This is how we do these by hand. And that's what we have to do, and why we learn all these different rules, finding rational factors, upper and lower bound test, Descartes' rule of signs. This is why we do all this, because you will do this by hand, not having to rely on a graphing calculator. And you will have to do this by hand on your quiz and test for this chapter. So that is all for 2.4 day 3. Today we talked about complex zeros and the fundamental theorem of algebra. The fundamental theorem of algebra basically says that if you have a power of 6, you must have 6 solutions. Some of them might be complex, some of them might be repeaters, but you must have a total of 6 solutions. So whatever that exponent is how many solutions you must have when you're looking at polynomials. All right, thank you for watching and have a nice day.